Hi, this is Mark Weitzman. I want to do a brief tutorial on Lorentz transformation and index gymnastics. So this is, sorry about that. This is physics with friends, quantum field theory. And this is a brief tutorial on Lorentz transformations. And what I'll call index gymnastics. So when we were doing our session of a week and a half ago, bunch of students, they felt very uncomfortable with equation 2.5 here on the inverse of a Lorentz transformations. And some of them were like very vehement that this can't be correct, but it is correct. It looks funny, and but it's easy to show that it is correct. And as a matter of fact, one of the first things when I was reading the news this morning about GPT, the new version 3.5, I tested it, and so I asked it right away. I said, if lambda mu nu is a Lorentz transformation, what is its inverse? And after a few seconds, it said lambda inverse mu nu is equal to this, which if you raise and lower indices, you'll get well, you'll get this. This is how you define this raising and lowering, and you'll get the you exchange the indices and keep their positions in the up and down positions. It's right here. Lambda inverse mu nu is lambda nu mu. This is not a transpose. If you were to transpose, I'll get to that in a second. So if you understand this, as you can see, it goes through it. It gives this basic equation for Lorentz transformations, which I'll talk about in a second. And if you understand this, then, oops, I shouldn't have done that. Then the rest of this video you can skip. But I just want to go over this a little bit more carefully. So let me go back to the iPad. And so even though Sugneka uses G mu nu, I'm going to use eta mu nu in special relativity. And some of the stuff I'm going to do now is very, very basic. So I just want to, for those who haven't seen it before, and it might be, very easy to understand. So before I do that, I want to give some references. So I found that the best books to really learn special relativity notation-wise and in detail is often the first or second chapter of a general relativity book. So, for instance, John Carroll's book, he has a very good treatment in his general relativity book, Space-Time and Geometry. I think it's chapter 1. He treats this material. And If you go back to an old book, like this book, this does it in a more modern notation. The telephone book they call this, Meisner, Thorne, and Wheeler. They have treatments in chapters, 2 through 5, but basically chapters 2 and 3. They do more than you need at first. They do forms and everything, but it's the basic notation that you use in special relativity. And, this is Steven Weinberg's book, Gravitation. This goes back to the same era as Meisner, Thorne, and Wheeler, Gravitation and Cosmology. And just to show you that this equation is in fact, let me just see, somewhere in here he has that exact equation. I seem to have lost it. But anyway, he does these manipulations same way. And he has a treatment in this in his chapters, early chapters, on chapter 2 on special relativity. And there are a million more references, but I recommend the general relativity textbooks, early chapters. They do a really good job on special relativity. So in special, let me get back. That was a detour there on my references. Special relativity, the metric tensor. Using the, quote, East Coast Convention. And if you happen to be watching from abroad, this is the East Coast of the United States. Is given by eta mu nu minus 1, 1, 1, 1. Everything else is 0. And this implies that ds squared equal minus dt squared plus dx squared plus dy squared plus dz squared. So these are Minkowski coordinates. And, you don't have to use Minkowski coordinates. You can also write, ds squared equal minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. This is essentially spherical coordinates. But usually we use Minkowski coordinates because they're constant and unchanging. Also in Minkowski coordinates, eta mu nu inverse, which we'll denote by eta mu nu, same letter but with just upper indices, they're the same. They're not only defined the same, but they are the same because the inverse of this matrix is going to be the same matrix. Whereas if you were working in spherical coordinates, then you'd have like g mu nu is equal to minus 1, 1, r squared sine squared theta. And the upper components would be the reciprocals of these. So you'd have minus 1, 1, 1 over r squared, and 1 over r squared sine squared theta. So unless you're working in a spherically symmetric problem or something, it's usually much more convenient to use the Minkowski metric. So the dot product of 2 4 vectors, if you have a mu and b mu, 2 4 vectors, then the dot product is a mu B mu equals A mu B mu equals eta mu nu A mu B mu equals eta mu nu A mu B nu. I'm sorry. Okay, erase it. I'm sorry. Okay. So the definition of lower components is given by like A mu equals eta mu nu A nu. And also, so when you're raising and lowering components, A upper is equal to eta mu nu A nu. So you can always lower, if you have an equation, if you have a tensor equation, you can always lower, you can lower like a mu index and raise a mu index. They don't have to be on the same thing. So if you have like A mu alpha, let's say you have an expression B alpha nu C mu nu, you always, this is tensor expression because the indices that we're summing on, we're always using the Einstein summation convention, and there's always one upper and one lower index. So this is equal to, you can lower like the mu if you want, A mu alpha, B alpha nu, C mu nu, and then you can go A mu alpha, B alpha nu, C mu nu, etc., etc. You can always lower a pair, lower one and raise another of the same index. So for Lorentz transformations, we usually denote them by lambda mu nu, and this confuses people because there's an upper and a lower index, but that's just how we do it. And so the transformation would be something like x prime mu equals lambda mu nu x nu. Some books puts the primes on the coordinates, the letters, like they'll write x mu prime instead of x prime mu. That's, I don't really care which way you do it. And the main thing is we have to preserve the dot product of vectors. We have to preserve the metric. And so if you think of something like ds squared is equal to eta mu nu dx mu dx nu, and this has to be in the other coordinate system, the Lorentz transform coordinate system. The metric won't transform. I mean, I could put eta prime, but it's always going to be the same. That's like the identity matrix is the same in all coordinate systems. As long as we're working in Lorentz transformations and Minkowski coordinates, the metric tensor won't change. But dx prime u dx prime nu, so this is equal to eta mu nu lambda mu alpha dx alpha lambda nu beta dx beta, and this is equal to eta mu nu lambda mu alpha lambda nu beta dx alpha dx beta. So if you look at this part, we can relabel the indices here. This is just eta alpha beta dx alpha dx beta. Indices which are summed can just be relabeled. So this and this have to be the same. That's where we get this fundamental relation eta alpha beta equal eta mu nu lambda mu alpha lambda nu beta. And we can also write, we can derive in the same way, eta alpha beta is equal to eta mu nu lambda, let's see if I confuse myself. I want to keep these like that. Let's say lambda alpha mu lambda beta nu. So either one of these is okay. Basically you have two indices. You're summing on the metric with the two upper indices on two Lorentz transformations. We get the lower on the metric. And if we do the upper, we sum on the lower ones. Okay. Nothing profound here. But notice I can rewrite this. Sorry. I'm going to rewrite this in a funny way. I'm going to write eta alpha beta. See, when you do index notation, order doesn't matter. Write them any order you want and everything. Since you're working with components, the summation will take care of everything. But here, I'm going to change the order. I'm going to write this as lambda mu alpha eta mu nu lambda nu beta. Now this part works out well for matrix multiplication. We get the second index is a nu and we're summing on the first index. But this one doesn't work out. We're summing on the we need this mu in the second part here. But this is equal to lambda transpose. Now when we do the transpose, the only thing we're doing is we're switching row and column indices. When we have lambda mu nu, this is a row index and this is a column index. So if I want to switch row and column indices here, I write this as just alpha mu. And I have eta mu nu lambda nu beta. Now the matrix multiplication goes through because the mu works out fine. The only problem here is that it seems like we're violating our tensor index notations by having a summation on lower indices. They're both down, but this equation is actually correct because this is a lambda transpose. This is the covariant way of writing it, and so we can essentially write this multiplication as lambda transpose eta lambda equal eta. That's the fundamental way in which the metric tensor is transposed. When you do a lambda transpose and a lambda, it stays invariant. Now this is very similar to what we do in like orthogonal transformations. Orthogonal transformations in, let's do Euclidean space. So in Euclidean space, the metric is all ones on the diagonal, and it doesn't matter whether we use lower or upper indices, they're all the same. But what we need for an orthogonal transformation is if we take the dot product of a vector or the square, let's say x prime a, this has got to be equal to say we have a orthogonal transformation this is equal to OAB, OAC, XB, XC. And we want to get, what we want to get is XA, XA. Equal to XA, XA. So in order to do that, this over here has to be equal to del BC. Now, so what we're going to have is we're going to have OAB. This is the usual transformation that you see for orthogonal transformations. Del BC. This is just the identity matrix. So what we have is O equals I. But now we don't have O here because the order isn't right, but we can write this as O transpose. O transpose BA, and then OAC equal I BC. And now the multiplication works out, so we're left with O transpose O equal the identity. That's the orthogonality condition that you learned in undergraduate physics. And you can put an identity matrix in here, and you can see that it's the same. The difference is that under an orthogonal transformation, the identity matrix is invariant. Under a Lorentz transformation, the metric eta is invariant. Okay. Now let's just prove, just like they did in ChatGPT, that lambda inverse rho nu is equal to lambda nu rho. Now the first thing you might say is, what does lambda nu rho mean? Well, it's just raising and lower indices. So this is defined as eta rho alpha, eta nu beta, lambda beta alpha. So we raise the alpha with the rho. That brings the rho alpha index up here, and we lower the beta index with the nu. We don't change their positions, so we have a lambda nu rho. Okay. Now what we want to prove, in order to show that this is actually an inverse matrix, here's what we want to show. Lambda inverse mu alpha, lambda alpha nu. So this is matrix multiplication. Lambda inverse lambda is equal to del mu nu. It's equal to the identity. Okay, so let's just substitute for see if this is correct. We have to verify that. So let's just substitute for this definition over here. And you just have to keep careful control of your indices. Eta mu rho, eta alpha sigma, lambda sigma rho. As you can see, if you raise rho, you get, I wrote this wrong. Maybe I didn't write it wrong. Okay. The rho, that becomes a mu over there. And then we lower the sigma, it becomes an alpha. So that's eta alpha mu. So that's correct. This over here, we claim this is also equal to, by our definition here, lambda alpha mu. So we have this times lambda alpha nu has to be equal to del mu nu. Okay. So I have eta mu rho, eta alpha sigma, lambda alpha nu, lambda sigma rho is equal to del mu nu. Now we use that formula we have. We have two lower on the metric and two upper on the Lorentz transformation. So this is eta mu rho. This is eta nu row. So we're, I could, maybe you're more comfortable if I write this since the metric is symmetric. But either way, I'm raising the new index. So this is equal to eta mu. I'm sorry, this is equal to eta mu nu, which is equal to del mu nu. So that works out correctly. Remember, this is sort of using if I multiply eta inverse times eta, I'm going to get the identity index. So this is matrix multiplication, u and nu. Okay. So that is all I wanted to do today. It can be confusing a little bit, but after a while, you'll get quite comfortable with it. Thank you very much for watching, and I'll see you next time.